Thanks. And our next speaker is Jay Lofstead from Sandia, talking about metadata management to support scientific inquiry.
All right, so what I want to talk to you today about is the Office of Science project that I have going on right now. And it really fits in a lot with a lot of the things we've kind of been talking about the last couple of days and trying to figure out how do we make more efficient access to data that scientists need to be able to do their discoveries. So we have two different concepts that we really want to think about. The first one is attributes, and attributes exist in HDF5 and a lot of other file formats. But I really want to talk more about metadata. And metadata I see as a superset of attributes. So if we look at it kind of how it works in like an HDF5 file, you take an attribute and you connect it to something within the file. It's going to be somewhere in the hierarchy, and you say this is an attribute that somehow additionally describes some item. The metadata can be either that, or it can be something that is an entire derived value that would attach to it. And ideally, we really want to be able to not just attach it to a single whole item, but we want to be able to attach it to a subset of an item or a more abstract thing, such as a time step or a run even. A campaign would be great, but that's potentially thousands of files or more, or objects, however you wish to decompose things. So that's really the kind of concept we want to look at, is more that higher level piece that we then want to be able to drive down into how do we support that with attributes. And thinking about this, what I ended up realizing is that we've really had 3 generations of tools so far, because there's really been, how they work has been somewhat similar for different classes of tools. The first one was looking at file level metadata, and I'll go through these in a little bit more detail, just kind of give an overview here. The second one was looking at how do we find particular values within a variable, and then the third generation has been how do I identify a region, for example, like doing a bounding box tag. And what we're doing in this project is really looking at a next generation tool beyond that that's going to look at derived quantities. Provenance, as I listed at the bottom, is definitely left as an exercise to the reader, because that's a whole different class of things that had decades of work, and why provenance is not widespread is another interesting discussion, but we won't go there. So in terms of the first generation, there's a few things that would come up as easy examples. The first one would be like POSIX extended attributes. The real challenge here is that how they're implemented in different file systems varies a lot, and because of that, you really can't, if you want something portable, take advantage of all of the different features that a particular file system might offer. Instead, you get limited down to, say, a 1K size at maximum to be able to have something that you say is going to work on a different variety of file systems that you may encounter. And how you save those, if you're going to move from one file system to another, varies. So with tar, you have to do a special flag to save it, and other tools may not have an ability at all to save it if they didn't consider that as an option. HPSS, the tape storage mechanism that we use in a lot of our sites, it has the POSIX extended attributes, but what it ends up doing is it takes all of the metadata, or the file information that it has, puts it in a database, and allows you to query from it there. And because of that, you then have the ability to do some more rich interactions with it. Starfish is something that takes advantage of that, and what it does, and as a commercial product, is it takes that kind of a database generated from all of the things within your file system and allows you to attach tags to files. And while that is a relatively simple thing to do, it's also incredibly functional and gives you that first huge cut to say, is this something I'm interested in or not? And being able to eliminate most things with that makes it a fairly easy lift as a product, and at the same time gives a lot of value. Another example that I would give kind of in this early stages where it's kind of a very coarse-grained mapping would be the Joint Genome Institute. And what they've done is they've built a specific tool for their domain that's optimized for what they do. It's really nice because it gives them all the functionality they need, but it's not portable to other kinds of applications. So there's a lot of these kinds of domain-specific tools that exist out there, but when they try to port them over to other domains, much like workflow tools, they end up not working well, and they end up not being generally useful. What I would consider a second generation tool is something like Fastbit, where it says, how do I make it easier to find that specific value? And Fastbit's probably the best example that I would have there. SideDB, the only reason I don't consider that as good is that I don't think it's as widely used in terms of the indexing capability, and it's really more 2D data sets rather than the more flexible Fastbit capabilities. The nicer piece with SideDB is the SQL front end, and that makes it more convenient for people to be able to dig through and look for things. I put the attribute capabilities for all of our favorite IO libraries in this category as well because of how they end up attaching to things. So that's just kind of where, in looking at the capabilities, where the granularity of the attributes meet in terms of metadata. In terms of third generation tools, there's been a few of these. What they really are looking at is how do I do things like tag a particular region of data, for example, in a weather or a climate simulation, saying there's a storm at this location at this time step, and be able to say, here's a bounding box in this data so that I know exactly where to look. And or in a fusion simulation, you might say, where are the eddies that you're looking for, things like that, and that end up being something that's really much more specific than just a particular gross value across the data. And the nice thing with these is that you can then go through as you're doing an analysis and say, oh, this region's interesting. Or if you're doing a combustion simulation, say, this is the point where ignition occurs, and you can then say, in this region at this time step, ignition occurs, and then you can know going forward and backwards how to look at that to be able to figure out what kinds of things you want to be able to do to change what you're looking at. So these end up being very useful, but at the same time, they're much more complicated to use. SOMETA, which CERN was a principal on here, that was something that was developed to look at in terms of key value stores. The challenge that I know that we ran into in working on these kinds of tools with the key value stores is that searching the key space means that you have to be able to match in the key space reasonably. And if you have things divided down into chunks, and you have your chunk dimensions and location in the greater space in your key, and you want to be able to match something that doesn't align with those directly, that becomes a difficult task. And that's why we went in a different direction. Doesn't mean that SOMETA is not very useful, it just means that it has different parameters that it ends up optimizing for. Taggit from Oak Ridge decided to take another different approach and look at how do we integrate these features into the storage system, but that then ties you to the storage system. So that's not a particularly portable approach. So the next one I would mention, it really comes out of this biomedical image metadata manager system. And the key here is that they have a system that seems like it's more one of those first generation tools that's going to be able to tag images and look for a particular kind of disease pictures or something else like that. But if you kind of step back and look at it, what really ends up happening is that it's just an image management system that allows you to put arbitrary tags on it. The fact that it was developed in the medical community just means that those were the people who needed the functionality first. So they ended up creating a tool that really ends up actually being fairly generic and gives you a lot of functionality. So that's why I kind of included in this generation. The last one I'll list here is the one that I ended up working on. This, we called it Empress, and what we ended up doing was, instead of taking the key value approach, we ended up using a embedded relational database, and we took all of the key pieces, such as the size and location of your blobs, and what the tag types were and the tag values were, and just put them into relational tables, and then we're able to do real SQL queries on that. Because of that, we got very good searching capabilities, because if things didn't match directly, SQL's very good at less than, greater than kind of matching and selecting things out. It could also sort by things like time step. So that ended up giving it a lot more flexibility. Plus, we could then tag anything, because we didn't really care how it related directly to the data in the file. We just cared about where logically it was associated with things. In terms of mapping that actually down to the base data, what we ended up looking at was, how do we store the logical location information rather than the physical location information? So it was never about byte offset. It was more about, this exists in this part of the hierarchy at this time step in this file. And that way you get back to the direct data, rather than having that hard linkage that may end up changing based on where something's laid out or how things get adjusted over time. So some of the other things that we want to look at that would kind of go beyond what we've looked at already, and these would be things like long-term data archiving. And this is a problem that Sandia currently has, and we've been trying to find solutions for it, which is how I kind of got involved a little bit with the production side. And that is, they have people that come and they say, we had somebody about 10 years ago that was working on a project in this area, and it was on this topic. Everybody that was involved with it is no longer here. Can you help me find it? And they don't know. So they're trying to find solutions to that. But they also want to be able to dive down further so that if we have any kind of mission-related things and there's a question, and they have a report that they're looking at and they're saying, why is that? They want to then also be able to dive back into the archives and say, okay, here's all of the artifacts that are related to that. Let's dig through and find out so that we understand exactly where that value came from. So that way we have a bit more assurance in what we end up doing. So that's where the long-term data archiving comes in. In terms of the short, medium term, this really gets into more the campaign storage where you're looking at, did this run generate things that are interesting that I care about or not? And if it's not, then you can throw it away. If it does, then you want to be able to preserve it for later. So that's kind of a higher level kind of tagging. Provenance, I don't really want to go into it because it frustrates me about how much nice work has been done, but yet how poorly it's also been done because they haven't done it in a way that keeps the provenance and the thing that it's about connected in a way that's not fragile. So that's a completely different topic. So the thing that we haven't looked at yet is, for example, how do we look at some derived quantity? So if you have an atmosphere simulation and you want to know where the pressure gradients go in a particular direction, so you can identify something like either straight line winds or a storm, then you need gradient information, and that's not something that's stored in the actual data itself. That's a derived quantity. And what we want to be able to do in this project is to be able to support those kinds of questions. So in terms of a research focus, what we're trying to figure out is calculating these derived quantities have multiple problems. One is they take time. Another one is they can be as large or potentially even larger than the original data themselves. And we need to figure out, based on how people are going to use them, which parts do we store? How do we store them? Can we do lossy compression on them or not? How does that affect the scientific validity of them? Where do we store them? How do we pre-stage in data based on the activity that somebody is going to have over an analysis session? So if they know they're going to do some particular kind of inquiry, we want to be able to pull in the data that's related to the kinds of queries that they want to operate on the data. But again, it's not directly on the data, it's based off of these derived quantities. So all of these things end up tying together. So that's what we're trying to drive through and get a better understanding of. So here's some examples of queries that we'd like to be able to run. So if we have a fluid dynamics code, we want to say, where's the gradient greater than 10, for example? And this could, instead of saying in the third generation that we have a storm in this location, this would be able to tell us either we have a storm of a particular magnitude based off of like a vorticity, or it could look at that and say, oh, we have straight line winds in this area because of these high pressure gradients. And we'd be able to find both of them just based off this one derived quantity. So that's the other reason why we're looking at this, is we're trying to get to more general things that we end up annotating. That way we have broader use over longer time for these kinds of extra bits of work that we do to make the data understandable. The second one, if we have a particle and cell, we want to look at to see when the vorticity is not zero. So in other words, there is some spin occurring. And the last one, as I mentioned earlier, is where did the ignition happen early in the combustion simulation cycle so that you know that something was happening that caused it to actually kick off early. So that's the kind of thing that we want to be able to do. So this is what's been driving our work. And we're initially, we're starting with audios for the front end just because Oak Ridge is part of it. However, through IIT, through Shiny Sun here, we are also potentially trying to get HDF5 on the side as a separate example for the front end. We think that would be more interesting than having this one example, but have two to show this is kind of a general system. In terms of the storage management, we're going to use Hermes, again, from IIT, and then for the metadata management side of it, we're going to build upon the things that we had done in Empress previously and extend that out to be able to do some more of the, how do I store this metadata? Do I compress it? How do I compress it? Where is it physically located? Those kinds of things. So, and then I have kind of the questions there on the bottom that we're looking at in terms of individual things. So that's what I had to talk to you about today. So thank you. I'm just going to repeat for the, so what's my sense of using Spark and Hadoop for these kinds of things? I think those will be good tools for generating the actual derived quantities, and they could be done offline. It's more a question for us in terms of the driving is that we want to be able to generate the quantities. And we think that's going to probably be done in situ during simulation time many times, just because you have the data there in a high compute environment already. But later, if you can do it and you know what kind of queries you want to do, that would certainly be a good way to generate this additional information that we could then integrate into the system for sure.
Probably partially answered my question.
Yeah.
But the derived capacity is storing all those as a separate data set and storing them?
Okay, so that gets into implementation details, which I'll go into. So Søren asked how are we storing these derived data quantities? And there's multiple answers to that right now. The first answer is that we will store them as if they were an additional variable, and that just ends up taking up as much additional space as it does. But for something that's much simpler, say like min or max, then we can just fall back to our third generation technology, just put a tag on that block. For other things that are large data storage and we don't want to store that much, we're trying to figure out what kinds of lossy data compression we can do on those. An initial stupid, and I will admit it, stupid approach would just say, let's average the value across the entire block. And for things that don't have a lot of variability, that's probably perfectly fine. But for other things where that's the actual key piece you're concerned about, is probably not good enough. But that way we could collapse out an entire block down to a single value. So that's part of the investigation, is to figure out how do we balance that out.
So, I have if I create this chart, storage format.
Yeah.
And so, in your examples that you showed, have you seen? So, my first question is, what's the magnitude of tagging?
Right.
The size of data that you can see. And the second part to that question is, when you do SQL queries, can let you do really weird things and very powerful, but that could translate to really bad indexing for the storage. Actually, then you have to go and get some data that
right.
With your storage system. So, have you seen such cases or what's your thought?
Okay, so two questions. One is, what's the magnitude of the metadata storage? And the second one is, how do we handle the ugliness of going from the derived quantity back to the raw data? So in terms of the first one, that's a capability that doesn't really exist in production right now. So we've been guessing. We've talked to people and asked them, and they say, oh, I can't do that. I said, well, if you could do that, what would you do? And we give them examples of things, and they're like, yeah, that would be useful, and that would be useful. And we've run a lot of examples looking at that, and the overhead is in the few percent kind of range at most, just because the actual storage of the tags and stuff compared to the raw data size is really, it's essentially zero. So even with a large amount of them, it's not very much. In terms of that ugly mapping from the derived quantity calculation back to the data, that's actually kind of the key part of the project, is how do we end up managing that in a way that's reasonable? Because the big thing, as I mentioned, is we don't want to do it on a per query basis, because that's going to mess up your caching hierarchy. We really want to do it on a per session basis and say, these are the things you're probably going to need multiple times. So let's give them higher priority to stay in the cache or the higher tier. And then the other pieces that might be accessed a few times in a row, but never again, we'll leave them in the slower, and that will take longer, but it will be a better session overall. So that's part of what we're trying to figure out, what the right balance is. Yeah. Yeah. Right. So yes, a lot of this is derived from the original raw data. That's really the intent. Yeah. I'm just repeating as we're going along. Yeah. How do I do the metadata to? I don't understand the question. Can you give an example?
Let's say you derive all this
information
based on whatever. Now, do you have anything that's metadata? Whatever you have
So let me repeat again. So how do we end up using the generated metadata so that we can actually use it later? And that's really what the tool like Empress is for, is that it has all the tagging. Because it's in a relational database, we have very flexible query capabilities on it. And we can have additional tags as desired to give summary information that will let us then indirect 1 or 2 levels potentially to then be able to get back to the raw data. So I think we have a lot of flexibility potentially there, but that's part of what we have to prove out still. All right. Thank you.
Thanks.